Hello everybody. Welcome to a new series of the ContinualAI seminar. Today we have Diganta Misra, who is going to present his work on Anytime Progressive Pruning, as you can see from here. Diganta is a researcher at Mila and I believe also Stanley Research. So I'm very happy to have Diganta here with us today, and I look forward to hearing the talk from him. So Diganta, the stage is yours.
Perfect. Thank you so much for the introduction and the invite. I have been following the ContinualAI seminar series, and it has been really great to see a lot of different diverse papers being presented. So I'm really happy to have the opportunity to present my work. As Andrea stated, my work is titled Anytime Progressive Pruning. This is a collaborative effort by people from Miller, from Landscape, from IIT Delhi, and from University of Texas, Austin. Before I start this talk, I'll just briefly go over what we are covering. And please feel free to interrupt me at any point of time if you have any questions. So we'll first look at the motivation of the problem that we are trying to solve, and then we'll go a bit in depth into the design and algorithm of the novel paradigm that we are proposing, which is called as Anytime Progressive Pruning. Then we'll do in-depth analysis of the results that we obtain, which are based on some ablation studies and some interesting trends that we observe with the training dynamics. We'll also open the floor to some research questions that we highly implore people to explore in depth based on this paper. And we also conclude this talk with a reproducibility statement. Alright, so let's get into the motivation of our work. So the motivation is divided into three main categories, which are themselves very popular subdomains within machine learning. First of them, which is arguably the most important, is pruning. So if you are familiar with lottery ticket hypothesis or papers which are about sparse neural networks, then this will sound very familiar to you. So pruning is essentially the method of reducing parametric complexity by removing certain redundant weights, where the definition of redundant can be followed by some heuristic. For example, one of the most popular types of pruning, which is also used in the original lottery ticket hypothesis paper, was iterative magnitude pruning, where they sort the weights based on their magnitude, and they say lower magnitude weights are rather redundant, and hence they remove it. There are two fundamental types of pruning. One is structured and unstructured. For this particular paper, we are only looking at unstructured pruning. And there are also two algorithmic types of pruning. So there are post-training pruning, which is like you already pre-train a model and then you prune it and then subsequently fine-tune it, or you can do it iteratively, or you can do it one shot at initialization as well, which, and some of them include snip, grasp, and simple. For this paper also, we are much more focused on one shot at initialization pruning as compared to iterative pruning. We do have results for iterative pruning, but it's not the most important focus, so to speak. Alright, the next axis of our motivation is this new work which was proposed by Meta, formerly Facebook, and Miller last year. It is a new learning paradigm that they call anytime learning at macro scale. Anytime learning is quite a old conjugation of the classical online learning setting, where instead in anytime learning you are more concerned with having a learner that can perform well at any point of time during the training. So you have a big data stream, and let's say you're continually training on it. Ideal hope is that if you pick that learner at any point during the training on that stream, it should perform fairly well. So that is what anytime learning in general is, and What this paper particularly does, which they call as Anytime Learning at Macroscale, is they try to find the optimal wait time in that particular stream to train the learner such that it actually is a good learner. So if you see on the figure 1, which is plotted on the left, on the x-axis you have the time, the data stream. So let's only look at the magenta line and the blue line. So where the magenta line here states that if you just not train throughout the whole stream and keep collecting the data, and you train it at a single point of time after you've collected all the data, that is what is called as a tardy classifier. And you can see that across the whole x-axis, the error rate is quite high because we are not training at all, but then it suddenly drops because we train on all the data in a standard supervised setting. While the other end of that scale is the blue line, where you train on each new batch or each new sample of data that you're receiving, more like in a classical online setting. So what ALMA proposes is a balance between the two, and they try to find these optimal wait time, which corresponds to these mega batches of data. So they wait for like 10 time interval to collect a mega batch, and then they train on that, and then subsequently once they have the next mega batch, they take the previous mega batch train model and fine tune it on the next mega batch, and so on and so forth, which is what the red and the gold line represent, except in the red line the architecture is dynamically changing, which in their paper they are just increasing the capacity of the model such that they can accommodate the new information that they're getting with the more mega batches in the stream. So also one of the crucial hypotheses in ALMA setting is that the time taken to train on a mega batch is subsequently very low as compared to the time taken to receive a consecutive mega batch. So unlike in online learning where you usually see the sample once, here you can iterate over a mega batch multiple times. So you can do a standard training over a mega batch for like n epochs. So you can imagine each mega batch is basically an independent data set of sorts, and you're training as a standard training procedure on it, and then you get your next data set and you're training on it continually. So as the authors quote, learner in ALMA is that produces high accuracy, can make non-trivial predictions at any point in time, and limit obviously its computational and memory resources. So this is really important to understand that we are not only concerned with the final test accuracy after training on the whole stream, but we are concerned with the performance of the model at any point of time during this stream. So you can consider like ALMA to be maybe the integration of like the classical continual learning final test accuracy. So you take like the sum of all the errors across at each mega batch. So this is another one of our motivation for our work. The next very crucial motivation I personally believe for this work is the domain of active learning. This is arguably not as much popular as it used to be because of the growth of self-supervised learning these days. So in classical active learning, we have this budget constraint. So we have a label budget constraint, and we have this big set of data, but they are unlabeled. And based on our label budget, we use an oracle to label the more important samples, and you can follow a lot of different heuristics to define which samples are more important. And there are like several categories of these work. One of them is disagreement-based active learning, which is one of the most fundamental approaches. Yeah, so that is all for our motivation for our work. We will discuss our work based on these three domains that I just discussed.
Sorry, Diganta, can you just hide the Teams window? Like, click on hide here.
Oh, right. I'm not having my cursor.
Okay, yeah. Thank you.
Is it good now?
Yeah, perfect. Thanks.
Okay. So based on the domains that we discussed, let's look at the question that we're trying to answer. So the question is pretty simple and straightforward. So if you have a dense neural network and you have a particular target defined sparsity, what should be the optimal way of pruning the model in ALMA setting? So if you recall back in the slide where I discussed ALMA, they had this dynamic architecture graph, but they were increasing the capacity of the model because we are receiving new and new data. So you would ideally want more capacity to accommodate the more information. But in our case, we are rather interested in the reverse of it. We are more interested in how we can make the model sparse and how we can make it more efficient in terms of large sequences in an ALMA setting. So our answer to that question is the framework that we propose called as Anytime Progressive Pruning. Uh, let's see exactly what Anytime Progressive Pruning is in terms of its design. So this is the blueprint layout of our algorithm. In the next slide, I do have the exact algorithmic version, which I'll also go through. But let's see what is actually happening here. So there are some subtle notations over here, but they're quite easy to follow. So you have these cylindrical objects which are denoted with M with subscript of a number, so that represents your each megabatch. So let's say you have M1, which is your first megabatch, and you're given F theta, which is a randomly initialized dense neural network. What we do is we take the current megabatch M1 and we formulate a small subset from it, which is 20% randomly selected samples from M1 at the first step, which is M1 hat, and we pass the original randomly initialized network F theta and this new subset M1 hat to SNP. And SNP is our pruning algorithm of choice. It's a at initialization one-shot pruning method. So what we do is we pass the network and the subset from the megabatch to SNP, and it gives us F theta 1, which is a pruned at initialization model. So let's say you have a target sparsity of 80% that you want to have at the end of training a model which is 80% sparse as compared to the model that you started with, and your stream has 8 megabatches in total. What we do is we prune progressively at each megabatch by 10%. So when I'm showing a pruning at this first megabatch over here, it is not pruning it to the target sparsity, but rather pruning it to a fraction of the target sparsity, which is uniformly applied across all megabatches, such that when you reach the final megabatch, when you complete training on the stream, your model will subsequently be smaller to the exact target sparsity that you had defined. So once we have this pruned at initialization model, which is F theta 1, we then subsequently train it on the current megabatch M1, and we end up with the trained model, which is F theta 1 subscript 1. So now when we have this megabatch trained model, what we do is we repeat the same process. However, there's one subtle caveat. Since we have M1 from our past data, we simply concatenate it to the next megabatch data, which is represented here as M2 plus M1, and then we take the subset, the 20% random selected samples from this complete concatenated set. So in classical continual learning, this will be called as full replay. So you're using all the previous data in your current experience or a current task. And we do this for all megabatches. So if you have M3, then it will be M3 plus M2 plus M1, and you'll take the subsequent 20% random selected samples from that whole big set. And then we follow the same process of pruning at initialization using SNP, and subsequently training it on that concatenated set, and so on until you complete the stream. So this slide basically is the same as the previous one, except here we algorithmically define the whole approach. So as I said, you have a given dense neural network F theta. We have tau, which is basically nothing but your target sparsity that you're concerned with, and your replay is basically this Boolean operator which says whether you want to concatenate your previous mega batches or not. By default, it is always on. And we have SB, which is the stream of mega batches. And as I said, for each mega batch, we have uniform pruning. So we prune a fraction of the total target sparsity at every mega batch, which is defined by delta. So delta is basically a list of pruning values of pruning states for each mega batches in the stream. And the rest of the slide is, as I said, pretty straightforward. It is the exact same as the previous slide, except when we write over here pruning state is 0.8 to the power delta t. That is just a application perspective. It is not specific to the algorithm. So the way we do it in code is we just have 0.8 to the power something, and let's say a pruning state is 1, then you're pruning it only by 20%. So your remaining weight is 80%. So it's 0.8 to the power 1, so you have 80% remaining weights, and so on and so forth. So in our work, we apply a maximum amount of pruning to be at 4.5, 0.8 to the power 4.5, which is nearly 33% remaining weights. So you remove nearly 66% of the weights that you have in the model. Okay, so based on the design that I just discussed, let's see what actually the contributions of our work is. So to the best of our knowledge, our work is the first comprehensive study into pruning in an anytime learning framework, and specifically we are talking about ALMA framework. And to this extent also we propose a novel progressive pruning approach in ALMA paradigm, which we call Anytime Progressive Pruning. We also do several experimental analysis and ablation study and compare it to standard baselines while also varying the sequence length. And when I say sequence length, it basically means the number of mega batches in the stream. And we do it for various standard vision models across CFAR 10, CFAR 100, and restricted imagenet, both at few and full shot. And we also investigate the dynamics of the training and the effect of different pruners when we have replay or we don't have replay. So with that being said, just a few TLDR before I go into the exact results. Whenever you see the mod operator, it basically denotes the size of a given set. So for example, mod of theta denotes number of trainable parameters in millions. And as I said, during the design, app always uses full replay buffer, so we always concatenate our previous mega batch by default, unless we specify otherwise. For all our experiments, the scope of the pruning was maintained to be global, which basically means that we do not define individual layer sparsity. We define a global network sparsity. So we do not care whether the model is pruning 30% of the last layer and 70% of the earlier layer. So it's just a global target sparsity. And 0.8 to the power tau into 100% represents the fraction of weights which are left from the initial dense model after pruning. So if your tau is 1, then you have 80% remaining weights as compared to the initial model. But if you'd like to represent it as the fraction of weights pruned, then you'd rather do it as 1 minus 0.8 to the power tau into 100%. Okay. Also, a couple of baselines for our work to compare against, because we, as to the best of our knowledge, we stated that we are the first to explore this setting in the context of pruning. We didn't have any adequate baseline to compare against, so we designed our own baseline that we feel is just, fair, and appropriate. And one of them is obviously the standard baseline, which is not actually pruning any part of the model. It's a model at full capacity and trained in a standard ALMA setting. So the original ALMA slide that I showed you, where you had one line, the gold line, which was representing the fixed architecture, and the red line representing the dynamic architecture, we are only taking the goal line model. We are not concerned with the dynamic architecture because in their case, they were increasing the model capacity. The other baseline that we call is Anytime OSP, which stands for one-shot pruning. So what we do is instead of progressively pruning the model by a fractional sparsity at each mega batch, this basically takes the model and prunes it to the target sparsity at the initialization before it starts training on the stream itself. So when I showed you the first mega batch where I was taking f theta and pruning it using SNP and using only M1, which is the first mega batch, I was in app, we were only pruning it to a fraction of it, but in OSP, we prune it completely to the target sparsity, and then subsequently we train on all the mega batches as a standard model. Just some subtle differences. OSP obviously is cheaper because it is already at the target sparsity since the start. So when you're training on a long stream, OSP will always have the lowest parametric complexity since the start of the training, followed by app and followed by baseline, which of course involves no pruning. And also there is some notation about the metrics that we use. So we obviously care about the final test accuracy, but other than that, we also care about the performance of the model at any point of time during training, which is the whole fundamental foundation behind anytime learning. So for that, the original paper of ALMA also uses a similar metric, which is called as cumulative error rate, which is basically the summation of all the number of misclassified samples across all the mega batches when you're finished training on a mega batch. So we have a held out test set that we use to evaluate the model's performance after training on each mega batch, and we take the number of samples that were misclassified and just keep adding that up. And that is what we call as a CER, and it is expected if your model is a good anytime learner, then your CER will be minimized. And we also use generalization gap as one of our other metrics, and it is the standard definition of a generalization gap. We just measure the difference between the performance of training and the validation. So remember, we had a very specific design of app, which might raise some eyebrows about why we did the approach that I stated and why not something else. So we did verify with our experimental setup that the design that we have is most optimal. So here the plot is basically showing the generalization gap and the validation loss for 4 different types that we tested. So the first one is app warm-up, which basically involves not pruning at initialization but having some warm-up epochs, like training the model for like 20 epochs in our case on a mega batch before we prune it. Then we have app default, which is the one I demonstrated to you earlier. We also have the one with weight decay, which we do not do very experimental analysis on. We do find certain benefits and certain disadvantages of using weight decay, but it is not within the scope of our paper. And we also tried app no replay SNP, which means that when we were doing replay, we were concatenating the previous mega batch to the current mega batch, and then we were sampling 20% random samples from the whole concatenated set. So here when I say no replay, it is not sampling from the whole set, but only from the current mega batch. But when it trains after being pruned, it is being trained on the complete concatenated set. We also tried app where we prune it at the end after training the whole model on the full stream and then prune it at the end. But unfortunately, that was very unstable, so it was not feasible to put it in the same graph, but we do experiment with the same. So as you can see from this plot, the blue line, which is app default, is extremely stable, and we see further up in our results that it does perform really well. And yeah, this is basically how we essentially came up with the idea of progressive pruning and the very specific design that I showed you earlier. We do some analysis as well in terms of the model's training performance. So as you can see, starting from the left, we have a plot which denotes the validation loss for ResNet 50. This is on a CFAR 10, and uh, the x-axis represents the number of steps across all megabatches. So in this case, it is 50 megabatches, I presume, and you can see that the validation loss of app, which is the blue line, is trending significantly downwards as compared to baseline and OSP, which is sort of stagnating. The second part is probably not very important, though I would understand that there might be some questions about the blue line having so many oscillations, which I will get to in some time to explain why we are seeing the oscillations. We have some very intuitive hypothesis behind that nature that we are seeing in the training dynamics. And as I said in our design, we by default use SNP, which is pruning at initialization method, but we do try with other pruning methods like magnitude pruning, random pruning, and grasp. So as you can see in the absolute rightmost plot, when we go from left to right in the x-axis, the parameter complexity is decreasing, which is basically denoting the number of megabatches. And you can see for both CFAR 10 and CFAR 100, magnitude pruning and SNP perform consistently better as compared to random and pruning and grasp. Even though we see that random pruning and grasp pruning do start out well for a few megabatches, eventually when you come towards the end of the stream, where the target sparsity becomes larger, the the performance just drops off, as you can see from the plot. So we do some investigative analysis into the effect of different pruners, but our goal was mostly to design a very robust framework that can achieve pruning in such a setting, which is why we stick with SNP as our default pruner of choice. Now, onto our results. So the results are divided into a few sections. So first we'll look at short sequence ALMA, which is basically that the total stream has less number of megabatches, which in our case is 8 megabatches. And we'll look at the results for CFAR 10 and CFAR 100. This is a pretty overwhelming table. I can understand we trained a lot of models for this work. But let me highlight a few of them. So as you can see, we have three fundamental metrics: test accuracy, which is the final accuracy after training on the whole stream, then the cumulative error rate, which I defined earlier, and the generalization gap. You will see that there is a very common trend, which is that app usually improves test accuracy in most cases, if not all, decreases CER as compared to OSP and baseline, and massively drops generalization gap. So for example, if you go to ResNet 50 and you see the row for app and compare it to baseline, for CFAR 100, the generalization gap for app actually drops by 33%, which we consider very significant. And this trend is observed in all of our results, that app is able to keep the generalization gap as low as possible as compared to both OSP and the baseline train network. And you can see also from this table that we have tried out various different pruners, and we report the results for that. And you can see for random and grasp-based pruning, we do not achieve satisfactory results. In some cases, the training even collapses, in which case we denote the results with a dagger, just to denote that it is unstable training. In all of our setting, the final target sparsity is set to be 0.8 to the power 4.5, which is nearly 33% of the total model complexity. Okay. One more thing before I move to the next slide is that in this case, as I said, we have 8 megabatches for CFAR 10 and CFAR 100.
where our per mega batch, the total number of samples is 6,250. All of the results you are seeing here includes full replay. And the optimization schedule that we follow is a multi-step decay, where we only decay the learning rate by 10%, by zero point 0.1, I'm sorry, at only the first megabatch. So we start out at zero point 0.1, then in the first megabatch training itself, we decrease it down to 0.001. But for all the subsequent megabatches, we keep it at 0.001. So this is our first setting that we tried. But in this first table, we try using cyclic multi-step DKLR, where we do the same decay that I told you about in the previous table, but then when it goes to the next megabatch, it resets it back to the original state and does the same decay again. So it's just like a cyclic step function of sorts. So and that does improve performance, as you can see, across the board, like for all the baselines and our model as well. But general trend is sort of very consistent, even though you can see that for some cases the test accuracy is down by 1.7 or 1.3%. Do recall that our parametric complexity of the model is nearly 30% as compared to the full parametric complexity model, which is denoted by baseline. And you can see the same trend in generalization gap, where app reduces the generalization gap significantly across the board. And all of these results in the first table in the slide is using SNP for anytime OSP and app method. The second table below the first one is the one where we do the exact same setting as above, but we do not use replay. So we do not concatenate the previous mega batch to the current mega batch at all, either for sampling or for training, except the rows which are denoted by yellow, which actually is a different setting than the above one, where we instead use the same DKLR as the previous table, not the table in the same slide. But irrespectively, we see the same trend that app is not able to perform realistically well enough as compared to OSP and baseline when there is no replay involved. And we do have some intuitive hypothesis into why this is happening, but this is just a concrete analysis to prove that it is actually the case. Okay, so but across all our tables, we have a fixed target sparsity, which is 0.8 to the power 4.5. Now let's see results for moderate and long sequence. So here we define moderate to be like 25 megabatches, 50 megabatches. We even go as high as 100 megabatches, which we consider as a long sequence. So here we follow the exact same setting. We have a cyclic multi-step decay LR schedule, and all of our pruning methods use SNP, and we have mod SP denotes the number of megabatches, which is 25, 50, and 100. Mod MT denotes the number of samples per megabatch, which is 2000 for 25 megabatches, 1000 for 50 megabatches, and 500 for 100 megabatches. And you can see usually when the number of megabatches becomes larger and larger, app performance grows very strong. To the extent in the final row where we have highlighted the CER with green, you can see that the differential in CER is nearly 100,000. The test set here contains only 10,000 samples. So when we show that our CER is 100,000 lower than compared to baseline, it effectively means that we are classifying the test set 10 times more correctly than the baseline method across the whole stream, because our test set remains the same for all the mega batches. And you can see that in any case, the generalization gap is always significantly reduced as compared to the baseline method across all the three sequence lengths. Let's see some results on few-shot restricted ImageNet. The reason we use few-shot restricted ImageNet or restricted ImageNet in general, restricted ImageNet is popularly used for measuring robustness because it's also a subset of ImageNet, and it has only 14 classes, which is similar to CFAR 10 and 100 in structure. It is because our runs are very costly, because on each megabatch we train the model for 182 epochs. So you can imagine, when we have 100 megabatches, the total number of epochs that we are training a model on is 18,200, which is a lot. So this does significantly take quite some compute effort to complete the runs, and we obviously train all our models, including baseline and OSP, for this work. So unfortunately, we only have one result for the 224 by 224 image size based restricted ImageNet, but let's see at the 32 by 32 size results. So for the same, we have different sequence length. So mod SP represents the sequence length, like 10 is our lowest. Then we go to moderate sequence length, which is 30, and our long sequence, which is 70. And for each case, we have different mod MT, which is basically the number of samples that we have per megabatch, so which is denoted. And you can see that again, it is the same trend that we observe as our previous results on CFAR 10 and 100. We improve the test accuracy in probably all the cases except the one where we had 10 megabatches. We decrease the CER. In that one case where you're seeing the in mod SB 70, where the CER increased by 3,000, that was because at 1 megabatch, app suddenly became unstable for reasons that we do not fully understand, which is why for that one single megabatch, the CER got increased, because as I said, a CER is just the summation across all megabatches. But we do see, as clearly stated in our previous slides, that the generalization gap consistently becomes lower when you use app as compared to baseline or OSP. And recall again that app and OSP are nearly at 30% parametric complexity as that of the full baseline. And we have the same SNP as a pruning algorithm of choice for all these results. Okay, so here we can see the CER plot, how it changes across different sequence lengths. So from left to right, the left one is for 8 megabatches, the middle one is for 25 megabatches, the right one is for 50. This is for CFAR 10, and you can see the blue line, which is for app, is consistently always lower in terms of CER as compared to the red and the gold line, which represent baseline and anytime OSP respectively. This plot might be not a bit too interpretable because we are jamming a lot of points together, but it is basically the same setting that we have earlier. Now we are just showing it for the restricted ImageNet results that I showed you in the table, how the CER progresses. Even though it is not clearly visible, you can see that, like, for the rightmost plot at the bottom and the two leftmost plot, the blue line is consistently lower as compared to the yellow and the red line, which denote baseline and OSP. And this is the same plot, just interpreted in a different way, which is basically the individual error rate. So instead of summing it up, this is the number of misclassified samples individually at each mega batch. And you can see that progressively app is able to match or is consistently better than both OSP and baseline app. Based on those results, we, while training, observed some very interesting training dynamics. So as I said, one of the most important axes of our observation is the generalization gap, and we emphasize on it quite a lot. And we observe this very interesting trend that builds up during training on this setting. So here what we are doing is we are simply plotting the generalization gap as a function of the number of megabatches, and this is for CFAR 10. And you can see for blue line, it is always consistently lower as compared to both the red and the yellow line, which represent baseline and OSP. But you can see when we increase the number of mega batches and we go into 50 and 100 megabatch regime, which can be considered to be long mega batches, we go into this very subtle shape of the plot that develops, which looks like a kind of a phase transition like plot, which we show exactly here. So what is happening is for the initial set of mega batches, we are in an underfitting regime, and the generalization gap is quite low because the model is not learning sufficiently enough to perform well. And then suddenly we jump into this overfitting critical regime, and you can see that both the all the three peak in terms of the generalization gap in this critical regime, and then subsequently the generalization gap keeps on dropping. So the hypothesis uh, for this oscillation that I told you earlier about is that when you do progressive pruning, you are essentially modifying the model at the start of each megabatch. So it acts like an implicit regularization technique, and hence you sort of forget a bit of the previous knowledge that you had acquired with a completely different structure. Since now the structure of the model has changed, you have a small dip, or in this case it can be significant dip at the starting point accuracy, but it does recover quite fast, which is why you're seeing the oscillation. However, uh, it is quite interesting, and probably we do not have the best explanation onto why the oscillation suddenly stop after you get over with the critical regime. I mean, it does not stop completely, it does oscillate, but the magnitude of the oscillation is significantly lower as it was in the overfitting regime. But in general, this trend that you're seeing where it goes from the underfitting regime to the overfitting quite fast, and then just smoothly keeps dropping into this phase transition like plot, is actually consistent for all our analysis where the number of megabatches were quite large. And we see the exact same plot, like the trend in that plot, for the few shot restricted imagenet as well. So as you can see, for 70 mega batches, you have the exact same trend that we observed in CFAR 10. Even in the case of 30 mega batches, it has that initial trend. It hasn't dropped enough to show that phase transition. But in general, this trend is quite predominant when we have a very high number of mega batches. And as I said, one more caveat is that app, which is denoted in blue line, in most cases, if not all, probably all the cases, have a final generalization gap, or across all the mega batches, the generalization gap is significantly lower than the case of anytime OSP and baseline. So we do investigate a bit into what actually is happening under the hood when we are progressively pruning the model using different pruners. So in this case, we only plot SNP and magnitude pruning because for our setting, SNP and magnitude pruning were performing the best as compared to grasp and random, which I showed you that they collapse after a few certain number of mega batches. So as you can see, the orange or the yellow bar here denotes magnitude pruning, and the blue bar denotes SNP pruning. And basically, each individual plot is the pruning that is done at each of the mega batches, and each bar represents that particular layer index, and the height of the bar represents how much we are pruning of that layer. So you can see that when we use magnitude pruning, initial layers are very heavily pruned at the initial mega batches, which we hypothesize to be bad because of the fact that we know that initial layers are very important for building accurate high-level feature representations, and pruning aggressively these initial layers might subsequently hurt the model in capturing these representation in the subsequent mega batches. So as you can see for app, rather it builds up from the later layers and then spreads out towards the initial layers, and is much more robust to the length of the sequence as compared to magnitude pruning, which is also why even though if you look at the table and see the results, the magnitude pruning might be very close in terms of performance to that of SNP. We still by default rely on SNP because of its ability to adaptively prune layers which are rather more redundant at initial stages. So based on everything that I've discussed so far, it might be a lot, but we do have some very interesting open research questions that we are very excited to at least explore, and we hope that people watching this or who will read our work subsequently will be also interested in exploring. One of them is how can we make app work without replay? So we are really interested in understanding the dynamics of pruning progressively, but not using replay, because obviously at the end of the day, we are concerned with reducing memory complexity, computational complexity. So it makes sense that we have an approach that can do progressive pruning, but not use replay. Then also, how can we make app work at extreme sparsity levels? So it is not presented in this slide, but we do have some results where we do pruning to an extreme sparsity, like something that you would see in a lottery ticket paper where they prune it to 95% sparsity. We do try something similar. We prune it to like 90% sparsity. However, in that case, app does not work. Which we are still trying to understand, and it would be interesting if we can develop a progressive pruning approach in this setting where we can make it work towards extreme sparsity levels. The next one is how can we form an analytical or maybe a semi-empirical understanding of the non-monotonic transition that we observed in the generalization gap as a function of number of megabatches. So as we saw the trend, when we keep increasing the megabatch, it forms that phase transition like plot. It would be interesting if we can actually develop some concrete foundational theory or some analytical understanding onto why that happens. Even though we have some intuitive reasoning, it would be very important to actually ground that reasoning for future work. The next point is more empirical and rather more applied, is that can we use this progressive pruning approach for maybe like some downstream task like segmentation or reconstruction, which would be also a very valuable contribution and will open the avenue of pruning and using sparse models in different settings. And finally, if we can analyze the impact of different pruning mechanisms in a more concrete way, as I showed you, we do analyze magnitude pruning as compared to SNP pruning, but if we there are several more ways of pruning, and if we can analyze all of them and make a more concrete validation, that would, I think, also be pretty important. With that, I would like to also highlight a reproducibility statement of our work. Our code is open source. It is on the link on the paper as well, and on the slides, which I believe will be shared after this talk. We have all our experimental logs open sourced on our OneDB dashboard. For this work, we train more than 400 models, which I showed in the tables where we denoted our results. To the best of our knowledge, we have optimized our code so that it is as compute friendly as possible, but we do encourage and are very welcome to accepting any new modification that can make the setting cheaper, because as I said, when you train on a long megabatch setting, it is quite expensive. It can take up to 15 V100 days to even finish one run, because the number of megabatches is large, and on each megabatch we're training on like 182 epochs. All our data sets are open sourced as well. We also provide clear instructions on how to download and set up and utilize the restricted ImageNet dataset, both in full and few shot. All our model definitions are also open source. We use models that are already well defined, and you can find them in the Torch Vision library. And we are definitely open to collaboration on the ideas that we discussed, or any other ideas that align to this work, or in general works of sparsity or progressive sparsity, or the setting of ALMA, because I think it's a very interesting setting that can be explored further. Just a snapshot of our dashboard. If you go in here, and you'll ideally see this. It's pretty easy to navigate. We have labeled all of our runs, so yeah, feel free to ask any questions like later on. Send me an email or something if you have any difficulty finding a particular run from this dashboard. In conclusion, we propose a novel progressive pruning approach in ALMA, which is called as app. We demonstrate the impact of different pruning methods, both with anytime progressive pruning and with the one-shot pruning baseline that we propose. We also analyze the impact of replay for app and OSP in ALMA. We analyze the training dynamics of app, OSP, and baseline under different settings, which is short sequence length, moderate, and long sequence ALMA, including a few shot regime as well. Our method also demonstrates a significant reduction in generalization gap, as I showed you, and most certainly, if not, reduces your total CER, and in most cases also demonstrates a strong improvement in test accuracy while being significantly smaller than the baseline model. Great, that is all for me. Thanks for staying with me, and if you have any questions, I'll be happy to answer.
Thank you, Diganta, for this talk. I think it was a very thorough discussion of the work. So let's open the stage, and let me open the chat so that if people here want to make a comment or a question, you can just open your mic and ask your question, or write in the chat, or even on YouTube. We will have like a bit of delay with YouTube stream, but you can ask your question also there. And while we wait, maybe I can start with one. So I'm not very familiar with the pruning techniques. So I was just wondering, what is the computational cost of pruning a network at each step, for example with SNP in this case? And I mean, if you can do this like online learning, so even doing it every few patterns, every few samples, so how does this impact on the training time, for example, if you have any comment on that?
Yeah, sure. So that's a good question, actually, because I probably missed out on some subtle details about the pruning, like the exact way pruning is done. So usually in classical literature, the way we do pruning is we have like a full network architecture, and we learn a binary mask, which is also the same size as the full network architecture. And then the binary mask has just values of 1 or 0, which denotes whether a weight needs to be kept for subsequent use or subsequent fine-tuning, or needs to be discarded. And whenever we do an operation, when I say sparse operation, what we do is we take this binary mask and overlay it on top of the full network, and then essentially you'd be able to use a network which is significantly sparser than the full model. But in terms of how much cost it incurs in our setting, where we use SNP, it is not as costly as iterative magnitude pruning, where in classical pruning papers, especially in locked-fit hypothesis, they actually require subsequent fine-tuning after pruning, and they require the first trained network. So they take an already trained network, prune it, and then subsequently fine-tune it. In our case, that is completely not required, and they do it iteratively as well. In our case, we only do it at initialization. So we only take the randomly initialized model or the previous megabatch trained model, and we prune it at the start itself, and it is not iterative, so we do not do any iteration on that pruning. SNP basically uses gradient signal information to find the weights which are important, and significantly applies that same binary mask that I told you about. So it is quite cheap to actually do this process of pruning even in very long megabatches. So we were actually trying to even run it for 500 megabatches, but we did not have enough computational resources to keep it running for that long. But even in that case, the pruning part of the whole algorithm was extremely cheap. So you can even do this in a lifelong learning setting, and you would ideally not have any major cost overhead for doing this. Yeah.
Yeah, that's useful. Thanks. Also makes sense. And when another curiosity, when you train the network, I mean, I know that training with deep learning frameworks, sparse networks with sparse tensors, I mean, it's very hard, right? So I guess in order to make it more efficient, you train like a dense network but filled with zero, so masking the weights, or are you actually training it with sparse parameters architectures?
No, so we use the same masking strategy that every other standard pruning paper uses. Like we mask out those weights, and we do not allow any gradient updates on those weights as well. And you're absolutely right. The reason why, even though I'm very probably biased towards sparse models and smaller models, it is not as popular, at least in general literature or like general usage, is absolutely, you're right, is the fact that sparse tensors, training sparse tensors based model on hardware is very hard right now, and also unoptimized. I understand there's certain companies like GraphCo, for example, they have their own chips called as IPUs, and they do claim that they have significantly better capabilities of handling sparse tensor based training, but personally I haven't tried it. So in our work we stick to the standard way of doing pruning and training a prune network, which is using masking.
Yeah, makes sense. Thanks. Was mainly my curiosity. So is there any question? Let me also check on YouTube if we have something. Yeah, we have a question from Antonio. Can you explain the difference between anytime learning and online continual learning?
Okay. Yeah, so this is quite debatable, to be honest. So at least from my understanding of what I have read is online learning is the setting where you ideally have a stream of data and you see the sample once. So you are not iterating on the same sample. So you do not do multiple epochs on that same sample. So you just keep seeing more and more samples as the model trains. And also, like in some sense, the objective of online learning algorithm is to have like the final test accuracy to be really good. But in anytime learning, we are more concerned with the fact that the model has the capability of iterating over a sample or a batch of samples multiple times. And the goal is to not just have a final test accuracy, which is really good, but also the fact that the model is really good at each stage of the training. Like after training on each batch or on each sample, it should be significantly better than its alternatives. So you can consider that the boundaries between online learning and anytime learning is really blurred, and it can look like online learning can be morphed into saying to be the same as anytime learning, but it's just certain caveats and jargons that is used in classical literature. Like, to be honest, I completely agree that it can be just labeled as a modified version of online learning or a different objective, just in the same online learning setting. Yeah.
Thanks for the question, for the answer. I think it clarifies the question. Do we have any other questions for Diganta here? Okay, if not, let's thank Diganta again for the talk. I think it was one of the few talks about pruning here, maybe another one or two, but yeah, it's definitely a topic worth exploring also for continual learning. So thank you again, Diganta. Thank you everyone for being here today, and I'll see you all next Thursday for the next Continual AI seminar. Thank you all. Bye.